How Light Shapes Your Body Clock, Episode 2, Why Cool White Light Boosts Alertness. In the previous episode, we learned about IPRGCs, their function, and how light affects the human circadian rhythm. In this episode, let's delve deeper into the relationship between light and the human circadian rhythm. We'll explore the specifics of light spectra, how light stimulates IPRGCs, and why cool white light is more effective at promoting alertness. 1. IPRGCs and melanopsin's blue light preference. Have you ever noticed this phenomenon? Cool white light tends to make you feel instantly more awake, while warm yellow light induces drowsiness. Why is that? The answer lies deep within our eyes, specifically in the IPRGCs and their highly selective sensitivity to light spectra. The light-sensing ability of IPRGCs depends on melanopsin, a specialized photopigment expressed within these cells. Melanopsin exhibits distinct wavelength selectivity. Its peak absorption sensitivity occurs around 440 to 550 nanometers, within the blue, cyan, and green light range. Especially when light contains blue wavelengths near 490 nanometers, melanopsin is activated most efficiently, triggering the strongest bioelectrical signals from IPRGCs. 2. The unique working mechanism of IPRGCs. Unlike visual photoreceptor cells which detect images, IPRGCs primarily regulate non-visual responses like circadian rhythms. Slow activation and decay. IPRGCs do not respond instantaneously to light stimuli. Their signal transmission starts slowly and fades gradually. High light intensity threshold. IPRGCs require relatively high light intensity to activate effectively. This ensures they accurately detect daylight changes without being disturbed by low-intensity light sources like moonlight or candlelight. Spectral specificity. They are most sensitive to blue light near 480 to 495 nanometers. 3. The spectral code. How color temperature reveals blue light content. To understand the alerting effect of cool white light, we must examine a light source's spectral power distribution, SPD, its spectral fingerprint. SPD is a curve or data set that precisely depicts the energy a light source emits at each wavelength. Color temperature, measured in Kelvin, is a common metric for describing a light source's color appearance, reflecting the relative proportion of blue to red light energy in its SPD. Low color temperature, for example, 2700 K, resembles candlelight or incandescent bulbs. The SPD is dominated by long wavelength red-yellow light with minimal blue light. Medium color temperature, for example, 4000 K. Similar to early morning natural light, the SPD is relatively balanced across wavelengths. High color temperature, for example, 6500 K, mimics midday sunlight. The SPD shows significantly higher short wavelength blue light energy compared to long wavelength red light. When comparing SPD curves of LEDs with different color temperatures, a clear trend emerges. The higher the color temperature, the greater the energy density in the 450 to 495 nanometers blue range, especially near the 480 to 495 nanometer sweet spot for IPRGCs. Interestingly, the same color temperature does not always guarantee identical spectra, especially for modern artificial light sources like LEDs. Due to variations in their light-emitting mechanisms, different light sources with the same color temperature may still have significantly different SPDs, particularly in critical blue wavelengths. Want to learn more? Leave us a message and our experts are happy to talk to you. 4. The secret behind cool white light's alerting effect. Now we can outline the biological pathway by which cool white light promotes alertness. High color temperature equals high blue light energy. Cool white light spectra delivers stronger energy output in the exact wavelength range IPRGCs are most sensitive to. Efficient blue light equals strong IPRGC activation. Light rich in the optimal blue range most effectively excites melanopsin in IPRGCs, generating intense and sustained bioelectrical signals. Strong signals equals melatonin suppression plus cortisol production. These powerful signals travel directly to the SCN in the brain, triggering a dual physiological response, suppressing melatonin secretion, which dispels drowsiness, activating cortisol production, promoting the release of cortisol and other hormones. putting the body in a state of alertness, focus, and quick reflexes. But is there light that stimulates IPRGCs even more effectively? Besides the blue light and spectrum, intensity and exposure duration also play critical roles in regulating circadian rhythms. Stay tuned as we explore these topics in upcoming episodes. Have questions? Leave us a message. Our experts are happy to help.